Well, I hope you've had a good time this evening. We have, I think, outstanding program for you to hear, and it's going to be introduced by two individuals that 2 years ago were flying pretty high and well above us, because about 2 years ago on Thursday they launched on STS-134 in the space shuttle, and they had a very important cargo on board. And this is the anniversary today, I think, of the installation of the alpha magnetic spectrometer on the International Space Station. A great day, and it's been a great experiment, and I think it's already produced some very significant results, and will continue to do so for hopefully a long time to come. And it is an experiment that I think will really make a difference, and certainly as you look at the space station and what it can do and what you can do with that kind of an instrument on board, it justifies the space station in itself. The two individuals that are here this evening were involved in doing the extravehicular activity, Michael Fink and Drew Fustel, and let me present them.
All right, thank you, Mr. Abbey and distinguished guests. It's been a great summit these past couple days, and we're delighted to introduce our very special speaker tonight.
Yeah, as George mentioned, almost 2 years ago today, actually this week, we were in space installing the alpha magnetic spectrometer on the International Space Station.
Hold on one second. And Mr. Alfred, or Dr. Alfred, that's why I couldn't come that 2 years ago. You kept sending me emails. Can you come to the Space Summit? And it's like, I'm sorry, I'm going to be busy. So I was really doing something. Sorry, Drew.
Yeah, so we were in space, and we were fortunate to be involved in that mission, and I think the only reason we flew in space was actually to install the alpha magnetic spectrometer. So we're happy to be here tonight to introduce our distinguished guest, and happy to talk about the mission a little bit.
So our guest tonight is the principal investigator for the alpha magnetic spectrometer. Professor Sam Ting is a very well-known and very respected particle physicist whose accomplishments are abundant. After his studies at the University of Michigan, his research took him to the European Organization for Nuclear Research, which has become CERN, Columbia University, and the Deutsches Elektrosynchrotron in Germany. And he arrived at my alma mater in MIT in 1969, where his work led to the Nobel Prize for the discovery of the J particle. A Nobel Prize, ladies and gentlemen.
So he certainly is a certified international man of mystery, but also of science. And more importantly, he was a great friend of the STS-134 crew. I think we've got a picture of the crew here. So you'll recognize, Star Trek came out this week, and of course this is a characterization of the last movie, the first Star Trek movie that came out. So I'm kind of proud of this and feel like we're. I think just the other day you spoke to the new Star Trek cast, right? Is that right, Mike?
Yes. They have a lot more excitement in space than we do, and we don't really like excitement. We like it when it works, like the alpha magnetic spectrometer. You can see our commander, Mark Kelly, in the center of the picture.
So Sam invited the crew to Geneva to look at AMS, but before he let us see AMS and learn about it and learn about what we're going to do with it, he had to put us to the test to make sure we were worthy of going to space and installing it. So here you can see most of our crew. I think this is myself and Mark and Greg Johnson, our pilot, and Mike, out on this precipice. There's about a 300-meter drop on either side of us. We did this about an hour after landing in Geneva, and I think Dr. Ting thought it would be appropriate to go and test us out with our EVA skills and see if we could survive this. And once we did that, I think he thought it was okay to let us go take a look at AMS.
Yeah, so finally we did get to see the beautiful AMS as it was being put together. And also in the center of the photo, you can see Dr. Susan Ting, Sam's better half. And in fact, Susan is here tonight, and she's very, very much welcome, Susan. Thank you for coming. And Susan and Sam, of course, were kind enough to welcome us to their home in France. We got a chance to spend a little bit of time with them, and it was very good in team building.
So once the AMS was built and tested in Europe, it flew across the ocean and landed at the Kennedy Space Center, where the crew was there to greet it. And of course, Dr. Ting flew with AMS, and our crew was there. We were all very happy to see it in its place and be ready to be installed into Endeavour's payload bay. And then, of course, launch day was fast approaching, and Dr. Ting was there to see us off. And this picture was taken just a few hours before the launch. And then you can see he was really concerned about us getting to space, and he had to help Commander Mark Kelly put his boots on so that we were all suited up and ready to go, and we all got a great kick out of that.
Yeah, he made sure we launched on time, and sure enough, we did. Just over 2 years ago, we launched, made it safely to orbit, and you can see the AMS with a beautiful last flight of Endeavour. And it got safely installed on the truss of our beautiful International Space Station. And just a few hours after installation, the AMS started taking data. In fact, I was surprised it was just a few hours and not a few minutes. I mean, Sam waited for a long time, and his team, for over 16 years to start getting data. So we got it really quick. And just for perspective, in the top center part of the picture, you can see my buddy Drew Feustel up there as a spacewalker near the AMS. So you can see how Drew's a pretty big guy, but AMS is even bigger than Drew, and our beautiful International Space Station is even bigger than the both of them.
I remember Sam telling us, make sure you don't kick AMS while you're out there. So we were very careful as we were moving around. With successful installation of AMS and start of data collection, there was a lot of very happy people back in the Operations Control Center at JSC once we knew AMS was online, including Dr. Ting in the front of the photo.
And Susan.
And Susan's there as well. And this is a beautiful photo that was taken by our crew as we flew around the International Space Station once we departed with the shuttle, and got some wonderful pictures of AMS, and you can see it perched there on the right side of the image. And it continues there to this day, and we hope it has many, many more years to come.
Let's see if we can get our video up and running here.
Is it feeding?
And Kevin, our video, great. With audio.
Hopefully. We promise there's audio here.
Any chance we get some audio, Kevin? Please?
Mike, maybe you could sing the song that goes with this.
It's a great song.
We'll just pause for a moment.
Called Europe. Europe is one of our partners for the space station.
It is.
And for the AMS.
This is where we're going to do a skit. Okay, Mike, you go across to that side, and maybe we can play horseshoes across the stage or something.
Well, I guess we're not going to get audio. This was right before launch of Space Shuttle Endeavour's last flight. The whole universe was in front of us. Our crew got ready to leave and got on the bus. It was still dark outside, and quickly became light. There's our buddy Greg Shamatoff, Greg Johnson in behind. Sunrise came over calm ocean, and we got ready for launch. Engines lit. This was my first time in a space shuttle. This was Drew's second time, so he knew what to expect, but I was surprised how fast it launched off the pad. It was pretty amazing what the solid rocket boosters can do, and this was Endeavour's finest day. Your turn.
Yeah, for those of you who haven't seen a shuttle launch, a few people in the room have actually been on one, but it's quite an impressive ride.
Teamwork, commitment, and exploration.
Okay.
It is in the DNA of our great country to reach for the stars and explore. We must not stop. To all of the millions watching today, including our spouses, children, family, and friends, we thank you for your support.
It's a final countdown.
In Houston on the big loop, we're tally-ho with the station. Initiating RPM on my mark. 3, 2, 1, mark. Capture is confirmed.
Endeavor arriving.
Thank you very much for the great ride and safe delivery of AMS to the station.
Well, thank you, Sam. I was just looking out the window of the orbiter, and AMS looks absolutely fantastic on the truss.
Endeavor departing. Fair winds and fallen seas, go. Yeah, thanks, Ron. Appreciate all the help. It's a pleasure serving with you boys. Go Navy.
Up through the stony ground, there's no room.
As we come up on about our 200th sunrise of the mission, we can clearly see AMS now on station and ELC-3. Just want to congratulate the whole team on the ground and the Expedition 27 and 28 crews for all the hard work that you guys have put into this. We're the ones that get to see this incredible view, but you know, you're all with us in spirit, and this is really a new day for science aboard the space station. So thanks to all of you.
It's a beautiful day. The sky falls, you feel like it's a beautiful day. So let it get away on the road.
Houston, Endeavor, runways in sight.
Copy, Endeavor, runway in sight.
Destination in the mud.
122 million miles flown during 25 challenging space flights. Your landing ends a vibrant legacy for this amazing vehicle that will long be remembered. Welcome home, Endeavor.
Doesn't ring true. You've been all over, and it's been all over you. It's a beautiful day. So let it get away. It's a beautiful day.
Houston, Endeavor, we'll stop.
Touch me. Take me to
On behalf of my entire crew, I want to thank every person that's worked to get this mission going, and every person that's worked on Endeavor. It's sad to see her land for the last time, but she really has a great legacy.
see the world in green and blue.
And so, ladies and gentlemen, on behalf of myself and Dr. Feusel here, we're really pleased and excited to introduce to you our guest speaker tonight, Dr. Samuel Ting.
So maybe I should show a small video first. Now, before I show the video, I want to thank what's happening. I want to thank Mr. George Abbey and Professor Barbara Alford to invite Susan and myself to come here. Normally, I ask my younger collaborators to give talks, but I simply couldn't say no to George Abbey. And so, first let me show you how AMS is built. Took 16 years to construct. Let's see. people had to work very fast. This is to space qualification test in Holland. Went back to Geneva to change the magnet in the accelerator to test it. Was too big for a 747, so I have to borrow a C5. As SSPF in Kennedy Space Center. This little film actually won an award. So now let me share with you, one moment, about the first result of AMS. So two of the astronauts and their wives are here today. It has a size of 5 meter by 4 meter by 3 meter, weight 7.5 tons. It is a unique experiment on the International Space Station conducting particle physics research in space for next decades. It is a US Department of Energy sponsored international collaboration. It has United States, Mexico, Finland, Denmark, Holland, France, Spain, Portugal, Italy, Switzerland, Turkey, Romania, Germany, Russia, Korea, China, and Taiwan. And this could not have been done without the strong support of NASA leadership, particularly George Abbey and Mr. Gerstenmaier. And I will also want to take this opportunity to thank Neil Lane for many advices. This is not a cheap experiment. And I got this cartoon says, we have just decided launching money directly in space was cheaper, as you can imagine. The fundamental science on the International Space Station, you can simply visualize by realizing there are two kinds of cosmic rays traveling through space. Light rays doesn't carry charge. It has been measured, for example, by Hubble telescope. Light rays has been measured over 50 years. All our understanding about cosmos has come from light rays. But besides light rays, their particles carry charge. This is an unexplored region in science. Using a magnetic spectrometer on the space station is the only way to measure high-energy charged cosmic rays. The largest accelerator in the world has a circumference of 16 miles, using 17,000 superconducting magnets at minus 456 degrees Fahrenheit below zero. So this is the 17-mile accelerator. It produces particles of 7 trillion electron volts. But there is an experiment in Argentina with 1,600 detectors in an area of 3,000 square kilometers and measure the cosmic ray shower. By adding up the shower, you found the primary energy of 100 million trillion electron volts has been detected. This means no matter how large accelerator you build, you can never compete with space. One of the objects we want to look is search for antimatter universe. The universe began with the Big Bang. Before the Big Bang, there was vacuum. Nothing exists in vacuum. Therefore, after the Big Bang, there must be equal amount of matter and antimatter. Now the universe is 14 billion years old. The question we ask, where is the universe made out of antimatter? The existence of antimatter was proposed by the great British physicist Paul Dirac, received the Nobel Prize in 1933. He realized in the theory of relativity, as well as quantum theory, the mass always appears as square. That means can equal to m times m or minus m times minus m. And he asked, what is minus m? Therefore, leading to the theory of antimatter. So for a truly great physicist, getting a Nobel Prize is quite easy. So this is the discovery of the antimatter of the electron, namely positron. Exact same property as the electron, except opposite charge. Nuclear antimatter was first observed by my collaborators and myself, and this is the New York Times article a long time ago. Physicists produce antimatter particle in a complex form. We know a nuclear matter like deuteron is a proton and a neutron. The question is, can you produce an antiproton, antineutron combined together from antideutron? So now we know all the particles have antiparticle. In the universe, in space, we have helium, carbon, and so forth. The question is there an anti-universe which has anti-helium and anti-carbon? So the issue is not matter, not particle, antiparticle, but whether it exists somewhere an antimatter universe. Cosmic antimatter cannot be detected on Earth because matter and antimatter will annihilate each other in the atmosphere. That's why you have to go to space. Since matter and antimatter have opposite electric charge, to distinguish matter from antimatter, you need a magnet to measure the charge of nuclei by detecting the trace of charge in the magnetic field. Positive go one way, negative go another way. To put a magnet in space is not exactly easy because the magnet will one end to the north, another end to the south. And so if you put on the space shuttle, soon the space shuttle will lose control. So you have to figure out a way to have a magnet, it doesn't rotate in space. It took 40 years to figure it out. And it turned out to be very simple. Another scientific goal is to understand the origin of dark matter. We know 90% of the matter in the universe is not observable. And that is why it's called dark matter, because you cannot see it. A galaxy seen by telescope is like this. But if you can see the other 90%, and they may look like this. And this experiment take an act of the Congress to establish a law, H.R. 6063, in 2008, to authorize an additional flight to deliver the alpha magnetic spectrometer and other scientific equipment and the payloads to the International Space Station. It's a very simple device. We know particles are defined by their mass, charge, and energy. So the first detector, called TRD, identifies electrons and positrons. There are 9 layers of silicon device, slightly smaller than the size of your table, measure mass, charge, and energy. This is a detector called ECAL, measure the energy of electron positron, and this called time of flight, measure mass, charge, and energy. A magnet measure the sign of the charge. Ring image Cherenkov counter measure mass, charge, and energy. Therefore, mass, charge, and energy are measured 4 times. You have to remember, in space, if something goes wrong, you cannot send the graduate students to fix it. At the beginning, we decided to use a superconducting magnet. And so this is the build superconducting magnet. It used 2,500 liters of superfluid helium, 1.8 Kelvin, to cool it. The magnet was tested carefully once it's charged. And then you can measure the resistance. The resistance is nearly 0, 17 nano-ohm. The inductance is 50 Henry. This means its field decay is 1% per year. That means once it's charged, the field will decay 5% in 5 years, and you will require no additional charge. Very difficult to make. Finally, we made it. As I mentioned this morning, one of the reasons we decided to do that is because if you build a superconducting magnet in space, it's the only way you can go to Mars, only way that I know of. Because you have a solenoid in this way, radiation will be bent away, and there's no radiation inside, no radiation outside. Trip duration 3 years, and cosmic radiation outside the Earth's atmosphere, as I mentioned this morning, is 90 rem. Lethal dose is 300 rem, and this matches with this. Therefore, no need to come back. And so you need this kind of radiation protection. But a superconducting magnet was ideal for a 3-year stay on the space station as originally approved for AMS. However, in the last 4 months before we due to go to Kennedy Space Center, NASA decided the space station lifetime is extended to 2028 or 2020 or to 2028. The shuttle program was terminated, thus eliminating any possibility of returning and refueling AMS. So we're stuck. So in the last 4 months, we took the detector apart and changed to a permanent magnet, add more precision detector, and so we can stay in space station for 20 to 30 years with the same resolution because we added more detectors. And this is a very large group from Aachen, Germany, made the transition radiation detector, which identified positrons, electrons by transition radiation and nuclei by DEDX. And it took 10 years to build this detector. The silicon tracker, there are 9 planes, slightly smaller than the size of your dinner table, but the coordinate resolution is 10 microns, a very small fraction of your hair. The rain image Cherenkov counter has 10,000 photosensors, and therefore to identify the nuclei by the thickness of the radiation and the energy by the radius. Finally, we have electromagnetic calorimeter made out of 50,000 optical fiber, 1 millimeter in diameter, distributed uniformly in 1,200 pounds of lead, some in this direction, some in this direction. Therefore, it measures the gamma rays to 1 trillion electron volt. There's Mr. Abbey, and they come to visit us together with Israel Gavan during the assembly of the detector. I mentioned already, the detector was too large for 747, and fortunately we were able to borrow a C5 from the Air Force, which came from the United States and come to Geneva and take us to Kennedy Space Center. At Kennedy Space Center, the most important thing is to match AMS with the space station markup, and so make sure they will fit together. If you find this in space, it will be too late. This is a famous photo, and it's my support of NASA. During the liftoff, the total weight is 2,008 tons, and the AMS weight is 7.5 tons. And this is exactly 2 years ago today, when Endeavour approached the space station, May 18th, 2011. So on May 19th, it was installed at 5 o'clock. It took us 4 hours because we have enormous amount of channels. It's a very complicated detector. And at 9:35, we begin to collect data. How you collect data in space? The data is transmitted to a Tetra satellite, goes to White Sands, go to Marshall Space Center, go to AMS Payload Operation Control Center and Science Operation Center in Geneva, Switzerland. In the last month, I suddenly realized, gee, what happens if this communication breaks down? And so we installed a computer on board and convinced NASA to train the astronauts to use this computer. And this computer can store the data for 2 months. So the flight electronics for data acquisition, there are 30 computers to handle 5,000 pulse height. For this detector, detector is 212 computers handling 200,000 pulse height. And this detector, 32 computers handling 3,000 pulse height. So it's a quite complicated system. But one of the major challenges of operating on the space station is the extreme thermal environment to which the experiment is exposed. So this is AMS, and this is the radiator. When the sun is in here, this side is hot. When the sun is on top, this side is hot. When the sun is on this side is hot. Remember now, you're in vacuum. Another thing that would affect the thermal condition on the space station is the radiator position, reflects the heat, and the arrival and departure of Soyuz or Progress. Also, the position of the solar ray schedule detector. To provide a thermal control, for this detector, we have 24 heaters, 8 pressure sensors, 500 temperature sensors. For this detector, 8 pressure sensors, 32 heater, 142 temperature sensors. For this detector, 80 temperature sensors. Look at this detector. On the starboard, on the ram and wake port, namely on the 4 sides. In spring, of 2011, it's minus 10 degrees. Few months later, it's plus 20 degrees. So in a very short time, it changed 30 degrees centigrade. And so you have to keep them constant. So this is the control room. I remember we were quite busy. So when the management of CERN designed a control room for us, I simply didn't have time to talk to them. But just before we left for Kennedy, I thought better of it. So I said, maybe you should ask the architects to come to talk to me. And so there came 6 architects, and the CERN has budget €1 million to build this detector, and after talking to me, become 2 million. Mainly because I realized, like in this building, since we're going to be there for 20 years, it's better to have a high roof and good ventilation. So I mentioned there are 9 silicon trackers. The resolution is 10 micron. The question is, a detector's resolution has no meaning unless you know where it is. And so how do you align them? You align them by 20 lasers inside, and in order to make sure they do not move, the temperature must be within 1 degree. The outside temperature changes greatly. So how do we do that? We have a liquid CO2, use a pump, go to heat exchanger, and put the liquid CO2 to cool the electronics. And then become two-phase, liquid and gas, go to the heat exchanger, go to a condenser, and come back, become liquid. And so this is a very large volume detector. And with this, you can keep the alignment over 2 years for layer 1, layer 2, layer 3, all the way to layer 9, to within 1 micron, which is impossible to do before. So the lessons learned after 24 months of operating on the space station. The first, operating a particle physics experiment on the space station is fundamentally different from operating a ground experiment in an accelerator. On the space station, the thermal conditions can easily destroy AMS unless all electronics components and station parameters are constantly monitored to avoid exposing the detector to a dangerous condition from which there's no recovery. The second is operating AMS on the space station is also different from operating on a satellite because we have no control over the orientation, attitude, and beta angle, all of which affect the thermal environment. But there's required full attention of the experts so as to be able to communicate the approaching dangerous thermal condition to NASA Mission Control Center to request the change of flying conditions. So this is Drew, I think, already showed AMS. Now, to analyze the data, I've divided my collaborators into 2 teams, lacking of a better name, so I call one A, another Alpha. The A are the Germans, the Italians, the Turkish, the Portuguese. The Alpha are the Americans, the French, Taiwanese, Chinese, Swiss, and Spanish. These people analyze the same set of data, do not talk to each other, except at 11 o'clock on Friday, and they come to my office. And so we have a 2 hours meeting. These meetings, as you probably can imagine, are not exactly friendly. So let me show you one result, namely search for the origin of dark matter. Collision of cosmic rays produce positrons. This we expect. But collisions of dark matter will produce additional positrons. The characteristics of the additional positrons can be measured very accurately by AMS. So there are many theoretical work and shows if you have a positron fraction, meaning positron divided by positron plus electron, as the energy from 10 billion electron volt to 1 trillion electron volt, and this is what you expect from collision of ordinary cosmic rays. And this is what will happen if you have a dark matter particle which has a mass of 400 GeV. So the spectrum will increase instead of decrease, and then it will suddenly go flat, then suddenly drop off. If you have a particle of 800 billion electron volt, the spectrum will go up, become flat, and drop off. So the characteristics will be the spectrum doesn't drop off, but it will go up, then become flat, and then drop off. This is the characteristics of dark matter. So in the first 18 months of operation, we collected 25 billion events. 6.8 billion are electrons or positrons. So this is the largest set of positrons, electrons, more than what is totally collected over the last 100 years. So this is the data. This is the front view. This is the side view. A TRD is triggered, shows it's an electron. The 9-track bending measure the momentum and show it is negative. Rich measure the charge of the electron. The electromagnetic shower shows its electron and measures its energy. So this measured energy matches with this measured energy, and this axis matches with the incident axis. This is its electron, this is its electron. So you have 6 or 7 consistent checks. So this is our first result. This is the ratio of positron versus electron positron. The data first decreases and then increases, but then increases very slowly. So the data show the positron fraction is steadily increasing from 10 to 250 GeV, and the slope decreases by order of magnitude. This is very strange. It means you have enormous amount of positrons. The question is, where does positron come from? There are two possibilities. One is from astrophysical sources. If it's from astrophysical sources, you will have a fixed position. But if it is a dark matter, then you have no origin because it will be everywhere. So limits on magnitude of dipole anisotropy in any axis in the galactic coordinate system for positron to electron ratio shows it's close to 0, namely it's uniformly distributed. And this shows the positron fraction on a linear scale. These are the previous experiment, much larger error, ends about 100 GeV. This ends at 300 GeV. More important, the previous measurement, the error is about 30 times bigger, 10 to 30 times bigger, and shows the spectrum increases. The new data shows the spectrum increase, then become flat, no longer increase. So the important thing is what happened next. How quickly does it go down? So the axis of antimatter positron has been observed for more than 20 years and has aroused much interest. This is the first experiment to probe in detail the nature of this axis with high sensitivity and precision. They observed many phenomena in this positron fraction, so the origin will be understood. It is very difficult in accelerator to do a 1% experiment. To do so in space is extremely challenging. It's never been done before. It is an effort of the entire collaboration with the strong support of NASA which made this possible. There are many articles in newspaper, and this one is from Dennis Overby about the clue of the implication of our measurement, and this one from the Wall Street Journal, and this one from the Spanish. This is from a very distinguished German newspaper, and show you two also. And this is from the French newspaper, Le Monde. And this is La Repubblica from Italy. This is very interesting. This is a description of AMS, and says this is AMS. Italian newspaper has a lot of imaginations. It has nothing to do with us. I don't know why it's called AMS, but I didn't want to correct them. So, in the next few years, we are going to trace the origin of dark matter. We're going to look at the existence of antimatter and the existence of something called stringlets. We already see electrons of 982 billion electron volt, positron of 636 billion electron volt. This means very soon we're going to move from 300 GeV to 1 TeV, and to see whether the spectrum drop off, how quickly it drop off. So I mentioned we want to look for antimatter. Besides antimatter, there's something very interesting, namely called strange quark matter. We know from accelerators there are 6 types of quarks has been discovered. But it is very strange. All the material on Earth is made out of only 2, U and D. A diamond, like a carbon, 6 protons, 6 neutrons. The question therefore is there material in the universe made out of at least 3 quarks, U, D, and S? If you think about it, if there are 6 types of quarks, why everything on Earth is only made out of 2? Are there anything made out of 3? It's a rather fundamental question. And this can be answered definitely by AMS. But if you want to look for antimatter universe, you want to look for strange quark matter, the first thing you need to know is, can you map out the periodic table in space? Because this will be a check of your sensitivity. So this is the first time the periodic table element is mapped out. All the elements has been seen. It ends at z equal to about 30. We see element to z equal to 40. Every element is there, but it's difficult to plot in a log scale. It shows the detector is functioning accurately, and soon we're going to find out what is going on. So, I mentioned the largest accelerator is at CERN, 16 miles in circumference. The cost of the space station is 10 times the Large Hadron Collider. The Large Hadron Collider has 4 big experiments. On the space station, there's only one, AMS. The real potential of this experiment can be simply visualized by visiting the fundamental discoveries in nuclear particle physics over the last half a century. In the 60s, the highest energy accelerator is in the United States, in Long Island. The original purpose, or the expert's opinion, is that you can study nuclear physics. The discovery with precision instrument is they found out two kinds of neutrino, breakdown of time reversal symmetry, a new form of matter. In the 70s, the largest accelerator is 400 billion electron volt proton accelerator in Fermi National Laboratory. The original purpose was to look for neutrino physics. What was discovered was the fifth and sixth type of quarks. This electron-positron collider in Stanford in 1970s, the original purpose is to study properties of quantum electricity, namely how the electric charge comes from. What was discovered are quarks inside protons, and the fourth family of quarks, the third type of electrons. The large underground experiment in Japan, the original purpose is to study the lifetime of proton. What was found, neutrino has mass, therefore can oscillate into each other. Hubble telescope, its original purpose was galactic survey. What was discovered was the flat curvature of the universe and the existence of dark energy. So I've ruined your dessert by mentioning AMS, can look for dark matter, antimatter, strangelets. By the time we finish this experiment, what we really can see, nobody would know. Because exploring new territory with a precision instrument is a key to discovery. Cosmos is the ultimate laboratory. Cosmic rays, I already mentioned, can be observed at energies higher than any accelerator. So the most exciting objective of AMS is to probe the unknown, to search for phenomena which exist in nature that we have not yet imagined nor have the tool to discover. Thank you.